anything. And I think one team got fully disqualified because they built the rocket so unsafe.
Oh, wow.
It wasn't even allowed to fly.
Wow.
And I saw the rocket that they put together, and it was sad.
Oh,
It was just really, really sad. Last year was like the only team that really did an excellent job.
that's good.
Brandon and Zach and Josh Espinoza and the whole rest of the team did such a good job that they kind of really impressed people. So I hope that is what they remember more than anything.
That's good.
These guys have the ability to do good things. Hey, Josephine.
Presentation.
Huh?
How was your presentation?
Oh, it was good. We did a good job. So, yeah, it's sort of like the intro, so he kind of gets up and says, this is what we're gonna do. This is what last year did, you know, this is our, you know, competition that we're trying to get to or whatever, so. They, gave their presentations, whatever, Formula Valhalla went on Tuesday, and then we, I think we're pretty good. I mean, we'll find out for sure when there is a great backup for it, but he's hopefully giving us some feedback so we can figure stuff out. We have a problem or an actual proposal, written proposal we gotta do for tomorrow that we've spent like the last all afternoon on today. And probably for the rest of that after this class. Making sure that it's in and stuff so that I think it's more like a rough draft. And then we'll get notes back on it and then we can edit, change, make it better according to what Dr. Merrill gives us, and then we can present for like the dean, and hopefully they'll accept our offer for them. Which I'm told like they're all like last year's team asked for like 14,000 and they got 8. So like, yeah, we never get what we asked for. Yeah, I'm hoping like we err on the side of like last year was really successful, and the only reason they couldn't launch was because of COVID. And so it wasn't because the designs were good enough; they were more than good enough. And I'm hoping that they're like, yeah, we'll send you to that competition with a good amount of money, but I don't know how much rover test off in the past or whatever. I know, like Baja County always gets something like 20,000 or to do this stuff. So hopefully.
I've been meaning to ask, formerly you guys have ham radio operators, all right, Chuck?
What's up?
Question on
How do you guys get that license?
activity two. Trying to imagine what would the compressive load
Uh-huh.
in reality. Would that just be kind of similar to the person hitting the pedal anywhere?
Yep. Yep, that's exactly it. So the situation I was imagining is, so, you know, imagine the crank is kind of turned up to like 12 o'clock, and someone just kind of stomping down on the crank, just like that. So that would put like a force that's like right down the shaft of the crank.
Oh, okay. So instead of the crank being horizontal and then stepping down, it's vertical and.
Yep, it's vertical, and then you're just stepping down on it. Another instance would be the crank is horizontal and it just runs into something too. That's another thing.
Okay, or I was kind of picturing as well. I don't know if this has ever happened to you, but sometimes when like you don't see where the pedal's at, and your leg or your foot is behind the pedal, and then when you try to pedal, you accidentally kick it forward. So is that also similar to
Yeah, that works too. Yeah, and basically any force that goes right down the shaft of the crank, all that would work.
Okay.
Yeah.
Okay, thank you.
We started element order.
We did, yes, and so we but we didn't finish it, and so we're gonna finish it. Yeah.
Professor?
That's correct. That's good. Yeah, Thursdays are my calm days, and so I don't have any office hours, so I just have my 2 classes that I teach today.
Yeah.
And so it's peaceful. Although I don't see the sun, because the only other class I teach today is a fully virtual one, and so I just sit in my office. And so the last time I saw the sun was at 8:30 this morning when I got here.
Not missing much. It's still there.
Professor?
What's up?
Question for you for the crank thing.
Yep.
I had trouble doing the meshing for the the hex stomp, doing the hex stomp, because every time I would try to mesh, even no matter how small I make the element size,
Uh-huh.
it would say like could not mesh, error, try a different meshing. So I am
Yep.
with the tetrahedron or the triangle ones.
That's fine. And so I would say like over the history of this class, like I'd say maybe like 10-15% of students also like for some reason just on their computer, it just can't produce a hex mesh on this bike crank. And I haven't really figured out why, but it's but if you do it with TETs, it's fine. You can just mention in your activity report that said whenever you tried it, it ended up with an error.
Okay, thank you.
Yep. Mm-hmm.
Yeah, it's like. Are you Monday class with me or are you Wednesday? Wednesday. You're Wednesday. That was almost like a waste because he brought us on campus so that we could go down to the lab. So you got those. Yeah, no, I was like, okay. And then he let us out early. He was like, all right, go. Yeah, I remember. For us too. Oh, yeah, that's it. It was at least nice to see like Dr. Park in person for a minute. Yeah. Same with like Dr. Trainer. Last. Almost 2 years ago now. I had one at lockdown. Oh. Remember coming to campus as we did. That was the last time I came for Yeah. Oh, was it? Yeah, so that's kind of. Yeah. Like, oh, we're picking up where we left off and oh, yeah. It was God, I haven't heard 331, 421, 431. Yeah, so I don't know machine design and vibrations. That's not sure. That was fun. It was challenging, but it was fun. Like I thought it was worth for like vibrations and for like machine design.
What's up?
Quick question for problem 5 and activity 2. Did you want screenshots of the like maximum load that we found that it could? Like, it doesn't ask for them, but I
You don't
thought-
need a yeah, I don't need a screenshot for it, but just tell me what you found.
Yeah. Thank you.
Mhm.
Well, yeah, same. I mean, we were in the library for the whole day working on stuff, but I actually liked that because sort of forces you to do stuff. And like, whereas at home, like, oh, my couch is right there. The TV is right there. On my computer's on, I can watch the thing very well. I try to do it. It's like, yeah, it takes you like 6 hours to get something done. It could take you an hour here. So like, yeah. Oh, remind me to go by the shop tonight again before we leave. One of the guys from the Rocket Discord said he was going to drop off that little kid's rocket set or whatever, and he was dropping it off at the shop, but I don't think he's going to be on campus till after 5:30, so after he got out of class. So. So how many people are officially on Rover for senior design? Isn't that like a straight mechanical? Senior design?
Yeah, it's all straight. None of the controls are right. It's all.
They're all volunteers, right? Okay.
So as far as I know, 16,
16?
actually, sorry, 17.
16, okay, that's not bad. You guys didn't have to get reduced in size this year.
Mhm. But I know it's partially different from past years because the past, you know, when I first joined the pod, I
Yeah.
had about 30 something campus, but they're under the old.
Oh, they
Yeah,
were.
they were, but then they switched back to.
Was that the same year that we took statics together?
No, that was the year after.
Oh, that was
It was my
your,
second
oh,
year.
okay. Because yeah, I remember you were into like Rover then, but I was coming around the shop a little bit. I didn't remember seeing people
Oh, yeah.
on Rover and stuff, but
I never reduced to like by a lot.
they all gave us a story about the rocket team years ago that almost burnt the school. He was like, yeah, I went off campus for lunch, and when I came back or whatever, like somebody grabbed me and said, you, this is unacceptable or whatever, and apparently the team was trying to mix like pots and pans. They were trying to make their own fuel, and they were using like.
Quick question.
Sure.
For problem 6, where we're summarizing our findings, is it all right for us to also include a picture? of
Oh,
the-
please. Yes, please. Because it's, yeah, you should have at least one picture of the, of your results.
Does it matter what picture we use? Would you prefer?
Pick the one that you think shows the most important results. Yeah, so I was a little bit vague on purpose because I want you guys to think about, you know, out of the results that you have, you know, what's the most important that you would show to like a manager or something.
Somebody high up in the.
Okay, it's 5:30, so let's go and get started today, guys. All right, good evening, everyone. How's everyone doing on this fine Thursday? Good, excellent. Yeah, it's end of week 4, and so you know it still kind of feels like we just started the semester last week, but you know we're already really deep into it now. All right. Did we talk about the midterm project last time? Okay, so let me talk about that a little bit today. I always get mixed up because you guys are right now are kind of on the same track as my graduate finite element class, which I teach on Mondays and Wednesdays, and so sometimes I forget what I talk to you guys about, what I talk to them about. So let's talk about that in a bit. Okay. In terms of the plan for today, we're going to finish up our lecture notes on the meshing basics. Okay, so we had just a couple more pages left to go on that, and so we're going to finish that up, and then we're going to start talking about boundary conditions. Okay, so boundary conditions I consider after meshing, I think the most important those two are kind of the most important parts of doing finite elements. But the difficulty in boundary conditions is the nature of the difficulty that people have with boundary conditions is very different than meshing, and we'll talk about that when we get there. Okay, so let me talk about the project first, then while we're all here. Okay, and so I'm trying something new in this class. So usually in this class and for most of my classes, actually, I like to have 2 midterm exams. But for this class, since we've been focusing so much on ANSYS early on, I thought it didn't really make a lot of sense to have a midterm exam for this class. And so I'm trying out to have a midterm project, and we'll see how that goes. Okay. And right now, what my plan for the project is to basically have it be like a miniature version of the final project. Okay. And so the final project for this class, if you looked into the syllabus, basically what I'm going to allow you to do for the final project is to apply ANSYS or apply finite elements to any problem of your choosing. Okay. And so for those of you who are in senior design right now, you can choose to do finite element analysis on a design you're thinking for senior design. Or if you're part of one of the student projects here, like Formula or Baja or Rocket or Arrow, you can do one of those. So those are very popular. Okay. And so for the midterm project, I'm going to give you the problem that I want you guys to look at with finite elements. And I basically want you to complete a kind of a full finite element analysis. Okay. You can almost think of it as kind of like kind of like an activity, but like without the training wheels. Because so far for the activities, I've kind of been telling you kind of step by step what I want you to do for the activities. For the midterm project, you're going to complete a full finite element analysis without those training moves. And so you're gonna have to decide what you want to do for the mesh, what you want to do for the boundary conditions, what you want to do for the material properties, justify all those decisions, write up the results and all the justifications inside the report, and then submit that report. Okay. And so I'm still kind of, solidifying all the details in my head, but I'm hoping to get the specs to you guys by the end of next week. Okay. Because I do want you guys to finish up the midterm project before the midterm, and so just so that you don't midterm exam, just so you're not kind of dealing with two things at the same time. And I believe our midterm exam is slated for week 10 or 11. And so, I want to make sure that you guys have at least, 3, 4, hopefully 5 weeks to work on the project before the exam. Okay. But I'll get more details to you guys about that next week. Okay. Yep.
Would we cover fluid flow beforehand?
No. So unfortunately, fluid flow is going to be one of the miscellaneous topics in this class. And so I know it's usually well requested. And so I plan to do it kind of at the very end. But we're going to focus mostly on structures, just because we're learning finite elements at the same time as seeing how to apply to structures. And so I want to just focus on one thing. But another thing I wanted to announce is that I just did a really big file dump onto our Canvas site. And so if you look at the lecture notes folder for the on our Canvas site, you'll notice that all of the lecture notes that I have planned for the rest of the class are in there. And I also have a lot of lecture notes, which I call like appendix lecture notes, right? Right, and so all those lecture notes will have an A in front of them. Right? And so all of those lecture notes, we're not going to be able to cover all of them, unfortunately, but they do cover a lot of really interesting features within ANSYS and within finite elements in general. Okay, and fluid flow is one of them. And so if you want to take a look at how to set up fluid flow simulations, and you want to do it just from my lecture notes, you can look into the website and check out one of those handouts. Okay. So I designed a lot of those handouts to be, pretty self-contained. And so, you don't really need to know a lot of other finite element stuff to understand that. And so if you're looking for a specific topic in finite elements that you want to learn, you can start by going there. And, of course, you can come talk to me and, we can discuss more as well. Okay. Okay. Any questions on anything before we get started with the lecture today?
You said the appendix A files they all start with A.
They all start with A. Yeah. Yeah, so all my lecture notes, they're all numbered. And so that's the, those are the ones that we're going to cover for the class for sure. And then all the ones that either we're not going to have time for, or, I'll kind of put it near the end, all those have A in front of that for appendix. Yeah. Okay, all right. So if there's no more questions, let's go ahead and pick up where we left off. Because we left off at this, talking about element order. Okay. So remember, when you're setting your mesh and finite elements, you have to set this thing called the element order, which is a very important property of your mesh. Okay, and we started talking about what this really means. Okay, and so what the order really refers to is the order of a polynomial, right? And so the two options that you have for element order are either linear or quadratic. Okay, and what they literally refer to is a linear polynomial and a quadratic one. And what we were saying was that, the reason this is related to finite elements at all is that, remember, finite elements wants to find an approximate solution to the differential equations on your system, right? And the way it does this is that it first assumes what it thinks the solution is going to look like, and then it tries to find the best possible function of that type that satisfies the equations. Okay? And so the two options that you have for the assumed solution are either a linear polynomial or a quadratic one. Okay. All right. And I think compared to I think the way that most of us are taught to solve equations, this is kind of a very different approach, because normally we're given an equation, like a differential equation, and then we just simply solve that to the best of our abilities, and then from there we see this function is a cubic function, or this function is a fourth order function. This is very different because we kind of decide what our function is going to look like ahead of time, and then we try to solve it from there. Okay, but it's this kind of backwards approach that's what makes finite elements going to work as well as it does. All right. And so, next what I'm going to do is I'm going to basically illustrate to you what this choice will have, or what effect it will have on your finite element solution, and what are some practical implications that you can consider, or that you have to consider for for these things. But before I get there, are there just any questions on this? This is just kind of recap of kind of the last 5 minutes of last class. Okay. All right. And so, of course, the type of function that you choose will have an impact on your solution. Okay. And so let me draw a 1D example for you just to kind of illustrate, what this means. Okay. And so let's see, we have our 1D case here. And so let's say that we have a one-dimensional case. Okay. And let's say that we have a situation where we have a true solution that looks like this. Okay. Right. And so in red right here, what I've marked is what's kind of like the true solution to this differential equation. Right. If you have a linear function or a linear element, what it's going to do is that it's going to take this this true function and then try to fit a linear function on top of it. Right. And so a linear function might look something like this. Right. Right. And so it's going to do its best to try to find the best line that approaches that, that approximates that solution. Okay. On the other hand, if you have a quadratic function or quadratic element, it's going to draw a quadratic function. Right? And so a quadratic function has the unique ability is that it can actually curve, and so you can have some curvature to a quadratic one. Okay? And so it might look something like this. Okay? Right. And so what you can see from this example is that neither function approximates it exactly, and that's kind of the case that you'll get most of the time in finite elements. But the quadratic one is doing a better job because it has that natural ability to curve, for the solution to curve within the element. Okay. And so generally, your quadratic elements are going to lead to a more accurate solution. Okay. Right. But the downside to quadratic elements is that they're going to be a little bit more expensive to compute. Okay. And so remember the phrase that that a lot of finite element engineers use is that there's no free lunch, right? And so if you want something better in your solution, you're going to have to pay for it in some way. Okay. And most of the times that's going to be through some kind of added cost. Okay. All right. And so we know that quadratic elements are more accurate, but when would you generally want to use quadratic elements? Okay. And so the regions where quadratic elements really shine are in areas where you expect to see rapid changes in your solution. Okay. Okay. Right, and so if you have a place in your model where the stress concentration is changing rapidly, right, and so you go from an area of high stress to an area of low stress, right, then quadratic elements are going to help you tremendously in this case. It's going to capture that change really well. Okay. And so in the business, what we typically say is that when you have an area of the solution that changes rapidly, we say, these are areas where you have high gradients in the solution. Okay. Okay. And so whenever you have high gradients, that's where quadratic elements are gonna shine. Okay. Okay. Any questions on any of this so far? Okay. All right. And so another situation where quadratic elements are going to shine a lot is when the solution to your equation relies on derivatives. Okay. Okay. Right. And so for this point, of course, question.
Is it the same thing? I mean, like when a solution is changing rapidly, it's just the derivatives, right?
So it sounds similar. And so what I mean on the previous page is that, due to, maybe some loading or boundary conditions that you're applying, the solution itself might be changing rapidly. Okay? But on here, what I'm saying is if there are derivatives in the actual, governing equations. And so they're a little bit different. So these
Information versus the stress.
exactly. Yes. Yeah. And so actually, for this one, that's a good segue is that, the equations that we work with a lot in this class are the structural equations. And for those ones, we have this relationship between stress and strain that's kind of baked right into the equations. And in particular, let's look at strain, right? And so strain we know is computed as the derivative of the displacement, right? And so by solving our static structural equations, we need to be able to, compute these derivatives as part of our, governing equations, okay? And so in fact, because the structural equations rely on the strain so much, it's always highly recommended that if you're running any kind of structural simulation, that you use quadratic elements. Okay? I wouldn't say that you need it in every situation, but it helps a lot. Okay. Okay. And the exact reason for this is a phenomenon known as shear locking. Okay. Right. And so if you use linear elements for a structural simulation, what can happen is that inside each linear element, you're going to end up with a constant stress. Okay. Okay. And the main reason for that is the strain is going to be constant in each element, right? And so because the strain is computed from the derivatives of the displacement, right? When you compute the stress, that's also going to be constant, because for a linear function, right? If you take the derivative once of a linear function, you end up with a constant, right? And so if you use linear elements in a structural simulation, you're going to have each element is going to be constant stress, okay? And this, you know, could be pretty bad for a structural simulation, because in order to compute, you know, the appropriate strains and the appropriate deformations, what it really relies on is it tries to rely on, you know, seeing what the difference in stress is internally in your model, okay? And so what can happen sometimes is that when you use a linear element for a structural simulation, you know, this constant stress state will cause some of your elements to kind of lock up, right? And so what you'll see is that if you run a structural simulation with linear elements, then the deformations that you would get are kind of underestimated, okay? And that's not good, because whenever something is underestimated, it means that it's basically inaccurate. Okay? And particularly having something be underestimated is pretty bad, because if you're doing some kind of like, you know, factor of safety or some kind of, you know, reliability study, then if you kind of underestimate the deformations, then, you know, you're going to think that your structure is safer than it actually is, which is a really dangerous thing to do with finite elements. Okay? And so this phenomenon, when you use linear elements in structural simulations, this is known as shear locking. Okay. And shear locking is bad. And so you want to avoid shear locking whenever you can. Okay. And so because of the shear locking phenomenon, you know, most of the time you're going to want to use quadratic elements with your structural finite elements. Okay. And actually, you know, I just found out recently that ANSYS will actually warn you. And so if you try to use a linear tetrahedron for a structural simulation, ANSYS will give you a warning that says, you know, are you sure you want to do this for a structural simulation? And they actually tell you that they recommend quadratic ones, you know, strictly, you know, because of this. Okay. And so for most of the stuff we're going to do in this class, you know, I would say just go with quadratic, you know, just to be safe. You know, otherwise you could limit this. But if you're running a different kind of finite element simulation, like maybe a thermal simulation or a fluid one, that's when linear finite elements is valid. And in fact, you know, for most of the fluid simulations that I've done for my research, I've almost always used linear elements, just because it's just from an implementation standpoint. If you're implementing the code, it's a lot easier to do linear elements than quadratic ones. All right, any questions on this? Okay. All right, so there's one more topic on meshing that I want to go over, which is called mixed meshing. Okay. And this is going to be very relevant for the activity we're going to do next week. Okay. All right, and so up to this point, you know, we've covered, you know, a lot of concepts with regards to meshing, right? So we covered things like the mesh element size, the element shape, the element order, and skewness, right? And so all these are really important properties. And so, you know, the point I want to get across with mixed meshing is you don't have to feel like you have to apply the same settings to your entire mesh, okay? And in fact, you know, if you have like an assembly type of geometry where you have multiple different parts, you know, it's a lot of times it's going to be a good idea to, you know, mesh certain parts with certain setting and another part with other settings. Okay. So just to give you a quick preview, so on a week from now, we're going to be doing a finite element analysis of a signpost. Okay. And so it's one of those kind of signs that overhangs the freeway that tells you that your exit is coming up way too soon. Okay. And so, there's two main parts to this signpost. And so there's the cylindrical post, the thing that holds up the sign. And then there's a rectangular part of the sign itself. Okay. And so this is a situation where, like, for the rectangular sign, it's basically just a giant box or giant rectangle. And so you can very easily fit like a hexahedral mesh on that, on that geometry. Whereas for the post, because it's so rounded, you might struggle a little bit to get a hexahedron mesh on there because of its rounded edges. And so you might have to resort to tetrahedrons there. Okay. And so the idea with mixed meshing is that you can apply one set of mesh settings here and another set of mesh settings here, and that's perfectly okay. Okay.
Excuse me,
Yeah.
why there is no like circular meshes? If there were like circular meshes,
Mhm.
that would be like in those kind of shapes that would work better.
Yeah. So so you're talking about like why isn't there like a cylindrical element type? Yeah. There are, and so there are kind of very specialized element types for certain applications. A lot of those being like kind of the curved edge ones, or some very kind of specialized shapes. And so there are solvers out there that do have that, but in general, you can get around a lot of those shapes by just using tetrahedrons and refining enough. And so for a general software like ANSYS, and so that's kind of why they only give you those options. But they do exist, and for certain applications, then those make a lot of sense. Yeah. Mhm. Right. And so, we just talked about an example where the shapes of your geometry might be different in different parts. Okay. But, another common situation is, maybe you're more interested in the solution in a certain area more than you are in other ones. Okay. And so in those situations, you would want to refine your mesh, or you want to have a finer mesh in those areas. Whereas in the other parts of the mesh, you don't really care about the solution that much. You can have a coarser mesh over there. Okay. And so we did this in the first ANSYS activity. And so in the first ANSYS activity, remember I had you guys apply a specific refinement object, but there are different ways that you can do it too, right? And so if you notice, in all the assignments so far, I basically forced you guys to use a method object and a sizing object, right? And so, quite a few of you all have asked me, why are we bothering to create these objects when we can just apply those settings just from the mesh itself, right? And so if you left click on mesh, then you can set things like the size and the element shape and the element order from there, without having to select the geometry and go through all that stuff. Okay. The reason I'm showing you how to do it that way is that, with those method objects and the sizing objects, you can actually select different parts of the geometry, and apply different sizing and different methods, very easily like that. Okay. And so when you change the mesh settings from just the meshing, the top of the meshing tree, what you're doing is you're applying global settings that will apply to the entire mesh. Okay. But if you want to apply settings for just specific parts, then you would do that with specific sizing or method objects. Okay. And so that's the main reason I'm having you do that stuff, is just to just so that when we do it on next Thursday, then it's not a whole new thing for you guys. All right. Any final questions on meshing before we move on to boundary conditions?
Yes, just for the refinement, I kind of noticed that when you refine something, it kind of dictates the whole mesh on the part. So is there a way to kind of stop it at a certain place, or or does it just take over the entire farm?
Yeah. No, it's a good question. And so there's definitely different levels of, how much you can apply refinement. And so that refinement object that I had you guys use, there's the way it kind of works is that you can kind of define how many elements deep it goes. And so I'm not sure what the defaults are, but I think the defaults are, maybe 3 or 4 different layers of refined elements, and then it goes back to the normal mesh. I think you can change that. I think if you go into the advanced settings for the refinement, you can change how many layers that it goes on. But another way that you can do it is you can create what I like to call kind of like extra surfaces in your model. And so if you want to basically just refine an area, you can kind of like project like a sketch onto that area and then say, refine just here and then kind of leave everything else alone. And so there's a lot of ways that you can fine tune it such that, you get kind of the exact mesh that you want, when some of the default settings are not kind of doing what you want to do. Yeah. Okay. All right. And so that's, everything I have for meshing for now. Okay. And so hopefully, this gives a lot of context for, all the meshing, meshing stuff that we've been doing so far. Okay. And so now let's start talking about boundary conditions. All right. And so like I mentioned at the beginning of class today, boundary conditions, along with meshing, I'd say this is kind of the, kind of one of the most important things that you need to get right in order for your finite elements to be good. Okay. But the nature of boundary conditions is, of getting them right is a lot different because, actually applying boundary conditions is not that difficult. It's not like the mesh where the mesh will oftentimes it'll try to fight you and trying to get a good mesh. The boundary conditions will mostly do what you tell it to do. The difficulty in applying boundary conditions is figuring out what you want to tell it to do. Okay. All right, and so let's kind of give a definition for boundary conditions one more time. Okay? And so boundary conditions, what they do is they basically specify how your geometry is going to interact with the outside world. Okay? Right. And so any kind of external effects that are going to be acting on your geometry, whether it be like an external constraint or an external load, external force, right? You're going to encapsulate all those effects into the boundary conditions. Okay. And boundary conditions are necessary, right? And so if you try to run your finite element simulation without boundary conditions, ANSYS will be like, hang on, partner, we forgot something, right? And the reason for that is, both, you can think of it as both physical and mathematical, right? And so from a physical perspective, boundary conditions are kind of the thing that kind of makes your geometry or makes your situation do something interesting, right? Because without boundary conditions, objects would just kind of be floating in space, or they just be kind of chilling, right? And so as an example, let's take this dock cam right here. And so on Zoom, I know you guys can't see it, but it's basically just a projector, right? And so right now, it's just sitting here, it's just not doing anything, right? It's not until I actually, pat it very slowly so I don't get in trouble, that's when the dock cam actually does something interesting, right? And so it's not until I actually apply an external effect, that's when the geometry actually starts to do, interesting stuff that we can simulate in finite elements, okay? And then from a mathematical perspective, boundary conditions are needed because otherwise we couldn't get a solution to the differential equation, okay? And so let me do a 1D example here just to kind of show you, why it's necessary. So hopefully, everyone's taken 308, or, if you remember things from your math classes, okay? Well, this one's not too bad. We're just going to straight up integrate this, okay? And so let's say that we have a differential equation that looks like this, right? And so we have d squared u dx squared is equal to 3x squared. Okay? And so to solve this equation right here, what we're going to do is, we can just simply integrate. Okay. And so if I apply an integral on both sides, we apply dx on both sides, okay, then we can start to solve this equation. Okay. But remember that, when you're integrating like this, we're applying an indefinite integral. Okay. And so we're going to need to add an arbitrary constant. Right. And so we solve one step of this equation. So we have du dx is equal to x cubed plus c1. Okay. And so c1 is the arbitrary constant that we have, from the indefinite integral. Right. And so let's go ahead and integrate this one more time. Okay. And if we integrate one more time, then we get u of x is equal to 1/4 x to the 4th plus c1x plus c2. And so what we have here is the general solution to our differential equation here. Okay. And then in order to find the full solution, we need to specify the values of C1 and C2. Okay. And the only way that we can do that is by applying boundary conditions. And so without boundary conditions, or in other words, without, external forces acting on this equation, we won't know its full solution, until then. Okay, any questions on this so far? Okay. All right, so let's go ahead and apply some boundary conditions on this guy. All right. And so let's apply the following boundary conditions. And so let's say that we have a boundary condition at x is equal to 0. Okay? And so let's say that u of 0 is going to be equal to 18. Okay? And then next, let's apply a boundary condition on the right side. And so let's say that du dx at x is equal to 10. This is going to equal to -5. And remember, we need two boundary conditions because we have two unknowns here. Okay. All right. And so let's start with the first boundary condition. This one's pretty simple. And so all we're going to do is we're going to take our general solution and plug in 0 for x. And so we have 1/4, 0 to the 4th power plus c1 times 0 plus c2. Okay. This is equal to 18. The first two terms are going to cancel out because they're just multiplied by 0. Okay. And then we're left with just C2 is equal to 18. Okay. All right. And so now let's apply the second boundary condition. And so to apply the second boundary condition, we need to take the derivative of our general solution. Okay. And so we have du dx at x is equal to 10. And so du dx is x cubed plus c1, okay? And so we're going to have 10 raised to the 3rd power plus c1, okay? And that's going to equal to -5. Right? Right. And so if we perform the arithmetic, 10 cubed is going to give us 1,000. And so if we subtract 1,000 from each side, then what we get is c1 is equal to -1,005. Okay. And so we plug both of those in and we can specify our full solution now. And so our full solution is 1/4 x to the 4th minus 1,005x plus 18. Okay. And so this here is our full solution. And so, in a lot of ways, you can kind of think of this as saying like your solution to your differential equation is not complete until you apply these specific boundary conditions. Okay. And so the same thing with finite elements, right? And so your finite element solution will not be complete until you apply the boundary conditions on there. Okay. Okay. Any questions on this? Okay. All right. And so before we start talking about the different types of boundary conditions, I want to give you, a little bit of my, intuition for how I think of boundary conditions versus governing equations, because, I want to kind of make this distinction between them. And so, of course, the governing equation is refers to the differential equation that governs the physics, right? And so, when we say when we specify static structural within ANSYS, and so that's our governing equation is going to be a structural equation. Okay. And so these are kind of distinct from the boundary conditions. Okay. And so the governing equations, these are basically going to be solved on the interior of your domain. Okay. Whereas the boundary conditions, they're going to act, most of the time, 99% of the time, they're going to act on the exterior of your domain. The governing equations will determine how, how your simulation will respond to stress or respond to external effects. Okay. Whereas your boundary conditions, these are the external effects. Okay. Okay. All right. And so, in a lot of ways, what I think when I think of boundary conditions, I think of these as kind of like the inputs to the model. Okay. Because what's happening, physically is that, you have your physical object, okay? And then, when you apply boundary conditions to it or you apply external effects, then your simulation is going to react to those. And so what I can say, these is going to react to the inputs. Okay? And so when I think of boundary conditions, I think of them as kind of like the instigators. And so those are the things that kind of, will kind of initiate the action and kind of cause the interesting behavior to happen. And then the governing equations determine, how that reaction is going to take place or how the response is going to be. Okay. But without boundary conditions, your governing equations will have kind of nothing to react to, right? And so just like our 1D case, right? And so without the boundary conditions, our solution could be basically almost anything. Okay. Okay. And so that's kind of my, my intuition regarding boundary conditions. Now let's start talking about the different types of boundary conditions there are. Okay. And so there are two main types that I want to go over. Okay. And so the first type of boundary condition that I want to talk about are what I call constraint type boundary conditions. Okay. The fancy mathematical name for these are called Dirichlet boundary conditions. which, for this class is not strictly required knowledge, but it's good trivia. And if you were, if you ever read kind of, any of the finite element literature, they might use the term Dirichlet. Okay. And actually, yesterday, one of my students actually came up to me and said that Dr. Weiss actually uses the terms Dirichlet and Neumann conditions in her PDEs class. And so if you take 438, 538, she uses these terms. And so he told me it was really nice to actually see what they meant, because up to that point, they were just kind of equations to him. But constraint type boundary conditions, they're called Dirichlet, in case you were curious. All right. And so, the reason I call these constraint type boundary conditions is that they force or they constrain the primary variables of your solution to have a certain value. Okay. And so the key here, of course, is going to be primary variables, right? And so if you remember, on the day that we talked about the theory behind FEM, is that every type of governing equation or every type of physics that you're going to solve has a different primary variable, okay? And so for structural simulations, which is the one that we are working with a lot in this class, the primary variable is going to be the displacement or the deformation. For thermal simulations, the primary variable is going to be the temperature, okay? And then for fluid simulations, the primary variable is velocity, okay? And so any boundary condition, and so talking back about structures again, and so any boundary condition that forces the deformation or displacement to have a certain value, that's going to be a constraint, okay? And so in other words, what we're saying is we're constraining the displacement to be certain values. Okay. All right. And so I can give you a couple examples of these, okay? And so in our simple 1D case that we did at about 20 minutes ago, the boundary condition that we applied on U, which was the first one, that was a constraint type. Okay. Right. So remember, we applied a boundary condition which says that U of 0 is equal to 18. Okay. And so this is a constraint type boundary condition because our primary variable in this case is U. Okay. And so by forcing U to have a value of 18 at x is equal to 0, we're constraining the U to have that value. And so an example of a constraint type boundary condition that you all have been using in the activities is a fixed support. And so in both activities so far, I've had you guys apply a fixed support on one side of the geometry. Okay. And so what the fixed support is doing is that it's forcing the deformation to be 0 at that location. Since we're forcing the primary solution variable to have a certain value, then that's what makes it a constraint type. Okay. All right. Any questions on this? Okay. And so constraint type boundary conditions are really important because you always need at least one in your FEM solution. If you don't have a constraint type boundary condition, then then the solution can't run. Okay. And so the reason for this is that the constraint, kind of gives a reference point from which, all the rest of the solutions can depart from, okay? And so, that's kind of the mathematical description of it. But, the physical description of that is that without a proper constraint inside your solution, you're going to get some very undesired behavior. Okay. And so let me give you just a very quick example. And so let's say that we have a beam, but the beam might not be fully constrained. Right? And so let's say that we have a beam where it's supported, but it's supported by rollers, okay? Right. And so, we all know what happens if we apply a force in this direction on the beam, okay? The beam is going to start rolling, right? It's going to be making its way downtown, walking fast, something homebound. I always forget the lyrics, but basically you're not going to have a beam anymore. You're going to have a skateboard, right? And so this is an example of, what happens when if you have a structural simulation without a proper fixed constraint or a proper fixed support, is that you're going to get rigid body motion. That's not to say rigid body motion is bad. And so, you can definitely simulate rigid body motion in finite elements, but not in a static structural simulation. So a static simulation has to be static. Yeah.
So when you say FEM simulation, you just mean static structural?
So any FEM simulation. And so
okay.
Any FEM, you need to have some constraints, there present.
But mainly just for the fix or the one you were just talking about.
Right. Yeah.
Okay.
Yeah. So specifically for static structural, you need to have at least one fixed support there.
Okay.
But you need to have other types of constraints for other types of simulations.
So if you were to do a dynamic simulation, would you necessarily need one?
You would, but it wouldn't be as restraining as something like this. And so, for a static simulation, your fixed support has to stop all rigid body motion. And so for a dynamic one, you can have some, rigid body motion, but it still has to be fixed in space at some point.
Okay.
Yeah. So you can't just simulate something that's rolling off into infinity. Yeah. Yeah. So probably a common case that you would probably find is that instead of a roller here, you can have a pin. Okay. But you can have a dynamic situation where, maybe you're rotating this beam that way like that. And so that's fine. And so you can simulate kind of the centripetal force of the beam kind of rotating.
So just as long as it doesn't interfere.
Exactly. Right. Yes. Yeah. Mm-hmm. Okay. And so, physically, that's a good example of, what happens when you don't have a proper constraint. But this is true mathematically too. Right? And so if we go back to our 1D example from before, just because we're running a little bit behind, and so I'll let you guys try this on your own. But if you try to solve this solution without a constraint type boundary condition, you'll find very quickly that you're not able to. Okay, and so I'll let you guys try this. But if you change the constraint type boundary condition to a derivative one, okay, so let's say that instead you apply a boundary condition to that's going to be du dx at x is equal to 0. I'm going to say that this has to be equal to 0. Okay. And so if you perform this change right here, what you'll find very quickly is that it's going to be impossible to find a value for C2. Okay. And so this constraint type boundary condition here is needed. It's required. You know, otherwise we just don't get a full solution. Right. So other constraint type boundary conditions that work with static structure will be something like displacement. Okay. So fixed support is kind of a very special case where you set all the displacements equal to 0 at that place. But you can have things like a roller support in your FEM simulation. And the way that you would do that is you would supply a displacement boundary condition. And so with displacement boundary conditions, you can restrain certain components of the displacement to be 0, but you can also apply certain components of the displacement to be free as well. Okay. And so that's another option too. And so, I would say for most cases, you're going to want at least one fixed support in your simulation. But there are ways around it. So there are ways where you can apply just displacement type boundary conditions and still get, a converged result. It's just going to be a little bit more tricky. And so, for now, I would say that, just always try to make sure you have at least one fixed support somewhere in your model. Okay. Just to make sure that you get a valid solution. Okay. Okay. Any questions on this before we move on to the next type of boundary condition? Okay. All right. And so that's constraint type boundary conditions. Okay. And so the next type of boundary conditions that that we have are what I call load type boundary conditions. And so in case you're curious, the fancy math term for this is called Neumann boundary conditions. Okay. Which is, of course, named after the dude who maybe not discovered them, but formalized it into the theory. Okay. And so how do we define load type boundary conditions? Okay. And so if constraint type boundary conditions are anything that places a direct specification on the primary variable, load type boundary conditions are kind of everything else. Okay. And so you would use a load type boundary condition for basically every other kind of external effect that's going to have some kind of impact on your FEM solution. Okay. Okay. Right. And so we've seen a couple of these, in our activities so far. And so, we've seen the force boundary condition, we've seen the pressure one. Okay. And so all of those fall under this category of a load. Okay. Mathematically, when you actually look at the mathematical application for these boundary conditions, your load type boundary conditions are going to involve some kind of derivative of the solution. Okay. A lot of times it's not just a straight up, the derivative of the solution here has to be x, okay, which is what we did in the 1D case, but the derivative is there somehow. Okay. And oftentimes for physical FEMs, for FEMs for any kind of physical situation, your load type boundary conditions are going to involve some material properties to some degree as well. And so one example, that I can give you from the activity so far is that when you apply like a pressure boundary condition on a surface in your finite elements, what you're basically specifying is the stress strain relationship at that boundary has to follow this pressure. Okay, and of course, whenever you're talking about stress strain relationships, then the Young's modulus is going to be involved. Okay. And so the load type boundary conditions for that involve, first of all, it involves the derivative of your solution, which is the strain, and it's also going to involve the material properties as well. Okay, so mathematically, load type boundary conditions are often a little bit more complex, right? If you're implementing this in practice, but I think for many people, these are the ones that kind of make the most intuitive physical sense, because these are actual, physical forces or physical pressures that are being applied on your model. Okay. Okay. Right. And so, if you're, kind of strictly speaking, these load type boundary conditions are not actually required to get a solution to, a finite element simulation, but also a differential equation. Okay. Okay. And so you can get a perfectly valid, a perfectly reasonable solution to a both a differential equation and a finite elements one without applying any kinds of loads. Okay. And so as an example, if we take our 1D case from the beginning, okay, if we replace the second boundary condition, right? And so if we replace the du dx at x is equal to 10, okay. So I think this was -5. Okay. And so if we replace this with, let's say, u of 10 is equal to 500, okay, just arbitrarily, then you'll actually be able to solve that equation just fine. Okay. And so what this says is that, a constraint type boundary condition, you always need at least one of those, but the load types they're not necessary, to get a valid solution. But a lot of times you're going to want to apply it. That's how you intuitively kind of think of the outside world interacting with your finite elements. Okay, because a lot of times you think about what's the force that that's being applied here, what's the pressure being applied here. Okay. And so a lot of times, you're going to have these in your finite elements. And so, I'm not telling you to not have them. But, if you're talking about just from a purely, what's required, loads are not strictly required to get a valid solution. Okay. Okay. All right. Any questions on loads? Okay. All right. And so, let's talk about some of the common ones that you'll see in finite elements. Okay. And let's limit our discussion to just structural FEM because that's what we're going to do most in this class. So one that you've seen from the last activity is a force. Okay. And so the units for force would be newtons. and also pound force. Okay. Another common one is a pressure. Okay. And the units for pressure are going to be things like pascals or PSI. Okay. Another one that we that we haven't used yet, but it's in ANSYS, is gravity. Okay. And so you can apply a gravity force on your object. Okay. And so gravity, a lot of times we don't think of gravity as an external force because gravity is something that's kind of inherent to the body. But technically gravity is an external force because you can think of it as like the Earth's gravitational field applying a force onto the object. Okay. And so there's a way in ANSYS where it basically uses the density of your object along with the the acceleration due to gravity to apply a gravity force all through. And of course, units for this are going to be, well, it doesn't really have units because it automatically determines it based on its density, but gravity is a force, and so it has units of newtons and pound force.
That's something that can be tailored toward how far away from the center of gravity you actually are.
Oh yeah, yeah. And so you can you can specify, like, of course you can specify the density, and if there's different areas of different density in your model, you can specify that. You can even specify the acceleration due to gravity too. So if you want to do a simulation on the moon.
Well, that's what I meant. Yeah.
You can do all that.
Further away you get from the center of mass is less.
Yeah. Right. And so this just kind of scratches the surface. And so when probably you guys have seen it, when you right click in ANSYS and you say insert boundary condition, there's a huge list of things in there, right? And so these are probably the most common ones that we'll stick to most in this class, but there's a lot out there, right? And so like another one that that I haven't really tried all that much is you can apply a bearing force, right? And so if you have a kind of a cylindrical slot, you can apply a bearing force in there to kind of simulate a bearing kind of sitting inside there. Okay. And so there's kind of a lot of specialized loads out there. Okay? And so there's a lot more variety here than your constraint type boundary conditions. Right? And so the important thing, is to, first of all, don't be overwhelmed with all your options. Okay? And the main thing when you're selecting your loads and you're choosing what loads to put on your model is to be as physically consistent as possible. Okay. Okay. And so this is where the difficulty of boundary conditions lies, or what I should say, this is where a lot of people kind of mess up their boundary conditions. Okay. And so you really have to think about what's the physical situation, or what's the physical act or physical stimulus that's going to be acting on my model, and what's the appropriate load or what's the appropriate boundary condition that encapsulates this this phenomenon. Okay. And so most of the mistakes that people make with boundary conditions is purely just conceptual, right? And so, a lot of times people will run a finite element simulation and they'll get something that, either right away they can tell that, the results don't really make sense, or, they get results and then they go try it in reality and then, you end up with something different, okay? And the main reason for that is a lot of times it's not the mesh, right? Because the mesh is nice in that it'll tell you right away if you fucked up your mesh, and so that's easy to tell. But the boundary conditions, a lot of times you won't really know if you didn't specify your boundary conditions properly until it's kind of too late, right? And so, maybe not until you've actually built your machine, or maybe you've kind of fabricated your design, right? You won't know that, the boundary conditions that you applied are incorrect there until, something bad happens, right? And so when you're applying your boundary conditions, or when you're thinking about, what you can, how to actually apply this, think of the physical situation and think of, does my direction for this force make sense? Does my magnitude of this force make sense, right? And so, actually, some of you have already been thinking about this, with regards to the last activity, which is really great, right? And so with the last activity, I kind of had you do a little bit of this exercise by saying that, we have this 100-pound force that this guy is going to be putting onto this pedal, onto this crank, and I had you guys decide, what's the direction that makes the most sense, given that the crank is going to be turning around like this and it's going to be pushing down like that, right? And I know you guys are thinking about it for the compression test too, right? And so, I've had a lot of people ask me, when is the bike crank actually going to be in compression? So what's the physical situation that that corresponds with that, right? And so these are the right questions you have to ask. And so, I'm actually really happy that you guys are thinking about it, because that's what you need to think about with your boundary conditions. And so I will say that, for some situations, it's not going to be that hard to imagine that, I have a force coming from this way, and it's very easy for me to say that, let's apply a force in that direction. Okay. But a lot of times, it's not clear, right? And so you're going to have to make some assumptions. You're going to have to make some simplifications in order for it to work, with your simulation. Okay. And so for one example, let's say that you're doing a finite element simulation of a bridge, right? And on this bridge, there's going to be a lot of cars that are driving over it. There's going to be a lot of pedestrians that are going to be walking across it. You're going to have winds that are going to be, applying some load on there. The bridge itself has weight that it needs to support. Okay. And so, if we talk just specifically about the cars and the pedestrians walking over the bridge, right? You want to apply a force that kind of represents that, or maybe a pressure. Okay? But how you actually do that is going to be challenging, right? Because the pedestrians are going to be in motion, right? I would argue that it's not, it may not be physically accurate to put a pressure, even though you have force that's being distributed all across the bridge surface, right? From the cars and the people. But if you apply those forces mobilized to certain locations where people were standing, you kind of average it over a period of time. And the same thing with the cars, right? And so, there's a lot of kind of really fine-grained decisions that you have to make for situations like these. And those decisions are going to affect your results too. And so, trying to determine, what's the best, way to apply a boundary condition in that situation, a lot of times it's not trivial. Okay. And so, really, for the activities, a lot of the situations are going to be fairly straightforward, and so you don't have to think about it too much. But when you start to apply finite elements for your senior design project, or professionally, or for anything, really spend some time to think about what's the right boundary conditions to apply here, right? Because it's one of those things where if you really give it some good thought and kind of map it out really well, it's going to pay off a lot in the long run.
For structural stuff like your bridge example, for example. Bridges are like really, really large, so how many cars and people are just one aspect of it, or whatever, like the bridge's own structural gravity being pulled down, whatever, is another force that's kind of on it as well. Or can you stack loads
You can.
in that? Whatever?
You can. And so you can combine some loads together into one, right? And so I would say that maybe the cars and the pedestrians, you can group those together. But ANSYS kind of gives you the option to kind of separate everything out. And so for a lot of cases, it's even if it's two things that are going to be directly adding on top of each other, separating it out into different loads might give you, would be, I would say it would be advantageous because, if you wanted to just modify one aspect of that load, so maybe you want to model, 100 pedestrians versus 50, then you can go in and manually change that part without, without affecting other stuff. And so, ANSYS actually does it really nice where it gives you a very nice, graphical interface where everything is kind of laid out in an organized way. And so the more detailed you can do it and the more fine grained you go, it's going to pay off. It's going to pay off in the long run. Yeah. There's a limit, of course. And so, if you don't want to have 500 different loads on your model, if you can help it. So if you're trying to look for one specific one, you're going to be scrolling a lot. But, but generally, what I tell people is, if you can separate it out and say that this mode is for this phenomenon, this mode is for this one, that's going to be something that that's going to benefit you in the long run.
You said something about like averaging over time.
Yeah, and so like if you want to do a static analysis of the bridge, but the loads that are going to be on the bridge, they're going to vary with time based on how many cars are on there at a given time or how many pedestrians. And so if you take just like the average amount of pedestrians on there and their average positions, then that would be a good way. Exactly. Yeah. Mm-hmm. Yeah.
Going back to the gravity, so kind of like when you mean by using that as a load type, for example, going back to the projector, we wouldn't consider gravity on that flat surface, but perhaps where the camera's at.
Yeah, and so the way it works in ANSYS is that when you say that you want to apply gravity, then it's going to apply kind of force all throughout this model. And so kind of like element by element, it'll say, what's the mass of this element based on the density and the volume of that element, and then apply a force just on that element. So the gravity is actually distributed all throughout. And so gravity, it's, even though I consider it a boundary condition, it's actually not something that's applied on the outside. So it's one of those boundary conditions that's actually applied all throughout the model. Yeah. So it's a little bit of a strange one compared to the other ones we've been talking about. Yeah.
So we're able to apply gravity, but are we also able to apply velocity to the object as well?
So that's for dynamic simulations. Okay. And so for dynamic ones, and so we are going to do an activity on that. I think it's going to be the 5th one. And so for the 5th activity, we're actually going to simulate a car crash. Oh, cool. And so what we're going to do is I'm going to give you a CAD model of a car that's right about to hit a concrete wall. And so for that one, you're going to give a velocity to it, and you're going to see it kind of crumple up a little bit, and then kind of, yeah, that's a cool one. I kind of like that one a lot. All right, any final questions on boundary conditions before we wrap up for the week? Okay, all right, so I have a little bit more on boundary conditions that I want to cover. But besides that, we're going to start talking about material properties on Tuesday. Okay, so have a great weekend, everyone. Thank you guys for coming. Thank you guys for tuning in. And I'll see you guys next week.
Thank you, Professor.
Thank you, Professor.
Oh, what's up?
I think it's thanks.
Oh, you're welcome.
Yeah, I gotta go grab one.